Yeah. All right, can you guys hear me? Yes, hear me, no hear me? Doesn't, again, some nods. Yes, Owen can hear me, Aiden can hear me. Okay. I'm gonna try to record this on this computer, and it's gonna let me. Okay, awesome. Where are we at? It is 12:11. Okay, we are on. Let's do this thing. Yesterday you took the quiz ending chapter 11. There is no chapter 11 test this year. There is no chapter 12 quiz this year. There's just chapter 12 test, the last test aside from the final of the year. It is on sequences and series, something which I am assuming you don't have a whole lot of experience with. So I am assuming that this is relatively new to most of us. I am looking and I am for some sort of confirmation there, and perhaps I'm getting a yes, maybe. Okay, well, let me start the recording for Darcy. Hi, Darcy. And jump in and get going on this, which we have decided, yes, is pretty new for most people. A sequence is a function whose domain is the set of positive integers. In other words, there are no such things as f of 1.2. We are only looking for the first term and the second term and the 23rd term, not the 53rd and a third term here. So let's just jump in with the easy example here. They say f of n is 1 over n squared. Let's find what f of 1 is. That would be 1 over 1 squared, better known just as 1. F of 2 would be 1 over 2 squared. That would be 1/4. Next up comes 1/9, and followed by 1/16. Okay. Those are those first four terms. And they say ... We could go further. We could go 1/25 and so on. To kind of take care of some things that we're going to learn in the future here, they gave it to me in this form. This is what I call an explicit form. If I wanted to know what f of 100 was, I can just straight out plug in f of 100. 100 squared is 10,000. I would get 1 over 10,000. Write out the terms of the sequence. And as it turns out, these are the terms. The first term is 1. The second term is 1/4. The third term is 1/9, and so forth. And speaking of just drawing arrows, represent the sequence as a formula for its nth term. Well, really, that's what they gave me at the top, which is awfully convenient that I don't have to write anything else down, because yesterday my cat decided to barf on the bottom part of this page, and I'm not really looking forward to getting anywhere near it. So now I don't have to. Yay. Yay, cat barf. Okay, write out the first 5 terms of the sequence. Not my phone. Okay, write out the first 5 terms of the sequence and graph it. So a sub 1 is really 1 squared minus 1 over 2 is 0 over 2 is 0. A sub 2 is 2 squared. 4 minus 2 is 2 over 2 is just 1. A sub 3 is 9 minus 3, so 6 over 2. My answer is just 3. A sub 4 is 16 minus 4, 12 divided by 2, I get 6. and a sub 5 is going to be 25 minus 5, that's 20, divided by 2 is 10. So a sub 1 is 0. Really, I'm going to say a sub 1 is 0 there. A sub 2 is 1. A sub 3 is 3, which I guess is not there. It's actually there. A sub 4 is 6. And a sub 5 is 10. And don't connect the dots. Because if you do connect the dots, that would be implying that all the points in between are also part of this, and they are not. So it's really just those discrete points. Oh my goodness, my computer's shutting down. This could be bad. Come on, come back to life. Apparently it was unplugged. The good news is my other computer is still up and running. So aside from not looking at, I guess I'm recording on this computer as well. So so Darcy will be uninterrupted as well. Okay, so far, does it seem pretty reasonable and straightforward? I got some nods. I got a nod. Yes, yes. Okay. Moving right along, this -1 to the n minus 1, or sometimes -1 to the n, is a pretty standard trick that we do. Let's see how it works. So a sub 1, when I plug in a 1, 1 minus 1 is 0, -1 to the 0th is positive 1, and I'm left with 5 over 1, better known as 5. If I ignore this first little bit, this first factor, my next one would be 5 over 2. I'm going to write that, and then I'm going to look what happens. Okay, that's when n equals 2. 2 minus 1 is 1, and -1 to the first is just a negative. The next one is going to be 5 over 3, but since n this time is 3, 3 minus 1 is 2, and when I square this, it's going to end up with a positive and do nothing. The next term is going to be a -5 over 4, and the last one that I'm looking for is going to be positive again, this time 5 over 5, which I suppose I should simplify just down to 1. Okay, so this -1 to the n, or -1 to the n minus 1, it makes this sequence into an alternating sequence. It alternates between positive and negatives. Okay, you've seen things alternate before? Yes. Oh, I heard a comment there.
Would it make more sense to just like, because I'm kind of confused where you're like seeing this pattern from. So would it be easier to just like take 1 through 5 and plug it into the equation?
Absolutely. That's all there is to it.
Okay.
That is all I am doing. So I quit doing it here because I realized that that just kind of made it alternate. You guys have heard of the band AC/DC? No, I got a no from Jacob. You have not heard of AC/DC. That is impressive. Okay, the rest of you seem to have heard of them. All right, so Jacob and the rest of you, AC/DC is not just a band name, it is also something to do with electricity. No one knows what AC/DC actually came from. Nope. All right, AC is for alternating current. That is the electricity which comes out of the wall socket at your house. It is an alternating current, 120 volts, but 60 hertz, meaning it alternates from being positive current to negative current, just like these alternate from positive to negative 60 times per second. Okay, just things which are around you every day. Okay, so here is kind of a piecewise defined function. Here is kind of a piecewise defined function. If a equals 1, well, n is odd. So this thing is equal to -1. If n is 2, Then n is even, so I follow these instructions and I get 2 squared. I get a 4. When n is 3, I'm at -1 again. When n is 4, I'm at 16. And when n is 5, well, 5 is odd, so I'm left with -1. A weird pattern there.
Wait, I'm confused what you did. You're just plugging in 1, 2, 3, 4, 5.
That's all I'm doing. I'm plugging in 1, 2, 3, 4, 5 into this piecewise defined function, telling me that when n is odd, to make it equal to -1, and if n is even, make it n squared. So my next one would have been 36. Okay. Fun, exciting, not too hard. This can, on the other hand, be very difficult. Some of them won't be. Now, instead of going forward and they're telling me the formula and I have to just plug in the numbers, they're giving me the numbers. I have to figure out what formula works for it. So the first one, not so bad. What do you think it is?
N pi to the n.
Okay, n pi to the nth. So the first one should be 1 pi to the first. The second one should be 2 pi to the second, 3 pi to the third, 4 pi to the fourth. We okay with this? Great. What's next?
2n.
I heard 2n, and I think you're probably mean the correct thing, but I'm not quite sure you said the correct thing. You said 2n? Owen, yeah.
N squared.
N squared. So my first one would be 1 squared, which is 1. So no, I think you meant the right thing. I could be wrong.
2 to the n?
2 to the n, yeah. So my first one should be 2 to the first. Oh, that's 2. My second one should be 2 to the second. Oh, that's 4. And then 2 to the third is 8. So I felt like you said 2n. I'm not sure whether you meant that or 2 to the n. If that were the case, it would have worked for the first two, but my third one would have been 6. So, okay. So far, so good. What about part C? What do we got?
N squared over 3.
Okay, n squared over 3. It's kind of tricky that they have that 3 in there, making the pattern look like it does something different there. But if I wanted to make it look like everything else, instead of 3, I could have written that as
9 over 3.
9 over 3. And I will tell you that that is a tricky one. If you don't see the perfect squares, then you are not going to get this. Here's another set of initials for you. S-E-T-I, SETI. You guys know what that is? I gotta know. Paul, I don't know if you nodded there. It was like half a nod, maybe? You know SETI? Paul, you with us? No, no one SETI. All right, SETI, S-E-T-I, is the search for extraterrestrial intelligence. Okay, we beam a signal into space. And we figured the signal that we're gonna send, it's not like an audio signal. We don't go, hi. Instead, we send a mathematical symbol. We send out the perfect squares. And we look for an intelligent life who would recognize those as the perfect squares and send us back a kind of similar signal. Okay, because those just aren't found necessarily in nature. I think we do perfect squares and then we alternate with prime numbers. So we'll send out like a 1, a 3, a 5, 7, that kind of thing. Next up, on the top, what are those numbers? Just the numerator.
N.
Great. On the bottom, what are those numbers?
E to the n.
E to the n. And there's one other little bit in here.
something with negatives.
Oh, 1 minus
Yeah.
n?
It's one of those alternating ones. So I have some -1, and it's either to the n or the n plus or minus, doesn't matter, 1. Let's see which one it is. So if n equals 1, then this would be negative. So that didn't really work. I'm just going to switch it to a +1. It would be exactly the same thing if I said n minus 1. Or I could have left it at n and pulled a negative out front. There are many different correct answers here, but that looks like a reasonable one.
So is the n over e to the n being multiplied by?
Yes,
Okay.
by this. I'll put an or here. Maybe I want to say negative n over e to the n times -1 just to the regular n. Or a positive again, e to the n times -1 n minus 1. Any of those three things, perfectly acceptable. Maybe you want to write the -1 to the n plus 1 first. No, as I said, many different varieties of the same correct answer. Okay, this on the other hand, I'm kind of assuming that you have seen a little bit of before. Factorial. I got a half nod in there, a half nod. Now that nod turned into like a kind of a little bit of a roll there, but okay, still nodding, got a thumbs up. You guys have seen factorial. Okay, just to be clear, something like 4 factorial is equal to 4 times 3 times 2 times, technically times 1, but does multiplying by 1 do anything? Not really. So 5 factorial would be 5 times 4 times 3 times 2 times 1, etc., etc. A couple definitions. 0 factorial is defined as 1. And without a little bit of work with combinations, I really can't explain quite why we had to make that definition. But just realize that it is a thing. 1 factorial, it fits the pattern. It should just be 1. Oh, okay, it's 1. All right. So let's jump over here and see if we can do this. I'm going to make life easier on ourselves and do part B before I do part A. 3 factorial should be 3 times 2 times 1, which of course is just 6. The reason I want to do that first is because 6 factorial is 6 times 5 times 4 times 3 factorial. Admittedly, it's not a whole lot different in writing 3 times 2, but so it goes. I know 3 factorial is 6. 6 times 6 is 36. 36 times 4 times 5. 36 times 20. I think we'll end up with a 720 here. Your calculators will do these. So here's one of these blue calculators. Savannah, downstairs, I have my graphing calculator. If you want, we can walk you through how to do it on the TI-84s as well. So this is, let's see, 6. And this button right here, PRB, perb. If I press it and then scoot over 2 to the exclamation point, write 6 factorial, I hit enter, and it seems to agree with that 720. All right, 10 factorial over 9 factorial. If you do this the long way, you will be here forever. And if you do it the short way, you will just report the answer is
10.
10. That's all there is to it. Because 10 factorial is equal to 10 times 9876540. 10 times 9 factorial. Over 9 factorial. Goodbye 9 factorials. They just cancel out. This is 6 times 5 times 4 times 3 factorial over 3 factorial 2 factorial. Well, the 3 factorials cancel out. 2 factorial is just 2. So I can cross out the 2 and the 4 and make that into a 2. So it looks like I've got 30 times 2. It looks like I have 60 as an answer there. Okay, without doing a whole lot of hard work. All right, let's switch gears a little bit and talk about a second way to represent a sequence. This one is called a recursive formula, and I emphasize that prefix re, recursive, because in order to find a particular value, you're going to do something, and then you are going to redo that something, and you are going to redo that something again and again and again and again. So here we go. In order to have an appropriate recursive formula, you have to have a starting point. And I will tell you on tests and quizzes, I always get one person who forgets to write down the starting point. So write down the first 5 terms. Well, they straight out told me that a sub 1 is equal to 1. That was easy. Without knowing that, I'm never going to be able to find what a sub 2 is. I want to find out what a sub 2 is, so I'm going to make n equal to 2. Okay, so I'm just going to rewrite this and say a sub 2 equals 4 times a sub 2 minus 1. Oh, 4 times a sub 1. Oh, I know what a sub 1 is. It's 1. So a sub 2 is 4 times 1. A sub 2 is equal to 4. Now to figure out what a sub 3 is, I'm just using this formula again. I want n to be 3. I want to know what my third term is. It's apparently equal to 4 times a sub 3 minus 1. Oh, 4 times a sub 2. So a sub 3 is equal to
16.
16. All right. And really the bottom line here is that to get to the next term, all I'm doing is I am
multiply by 4.
Multiplying by 4 each time. I'm taking the previous term and I'm multiplying by 4. I get 64, and a sub 5 is 256, I believe.
How do you go from, because if a sub 1 is 1, I get that, but why is 4 times, how do you know that a sub 2 is 2?
Okay, so I want to find out what a sub 2 is. So I'm going to look here at my formula, which tells me, all right, to find a sub 2, I'm making n equal to 2.
N equal to 2.
Great. So when they say a sub 2 equals 4 times a sub 2 minus 1, what is 2 minus 1?
1.
1. So I'm really looking for 4 times a sub 1. Oh, a sub 1 is equal to 1. So I'm really looking for 4 times 1.
Oh, okay.
Hmm. All right. Find the first 5 terms of the sequence defined as follows. I'm going to go ahead and kind of do it silently. I'll leave my projector on. You guys can go ahead and try it on your own and see if we end up in the same place. And the only thing I'm going to say is they told me that a sub 1 equals 2. Hi, Harper. Sweetheart, Daddy's in class. All right. Apparently, we're going to have a little soundtrack here. So sorry about that.
Mr. Reeves,
Yes.
Maddie just wanted me to let you know that she got locked out of the room because of her Wi-Fi, and she's trying to get back in on her phone, but it's not showing up on the hub for her.
Okay. I will see if I can do anything about that from here. Kind of looks like we lost Santiago too, right? Oh, there he is. Well, I guess Maddie, I'm going to send her the recording as well. They're always available on YouTube if you guys look. I didn't do A sub 5 just because it got kind of nightmarish on me. Buggy, can you turn down the volume? Daddy's going to come turn down the volume, okay? There you go. There you go. I mean, what's a Thursday without a little baby shark in there? Okay. Do we get some of the same answers here?
Wait, Mr. Reeves, I don't understand how a sub 3 or a sub 2 is equal to 1/2.
Okay. Because a sub 2 should be a sub 1, which is 2, over 2 squared.
So then how is a sub 3 1/2 over 3 squared?
Okay, so a sub 3, and I'm going to write off to the side, a sub 3 should equal a sub 2 over 3 squared. Well, a sub 2 is 1/2 divided by 9. 1/2 divided by 9 should be 1/18.
I guess what I don't understand then is how do I don't understand how a sub 2 is 1/2 if.
Okay, so a sub 2, let's write it down, a sub 2 equals a sub 1 over 2 squared. Well, what was a sub 1?
2.
And what is 2 over 2 squared?
Oh, 1/2.
Yeah.
Okay.
I mean, a sub 5, if we're interested in, should be 1 over 288 all over 25, which, again, sounds something like a nightmare.
1 over 7,200.
Yep, that's it. Because instead of dividing by 25, I divide by 100, and then I multiply by 4. So 4 times 1 288 is 72. Multiply by 100, we get that 1 over 7200. So the numbers aren't that diabolical or anything. Okay, the next time around, they tell us not what just the first term is, they tell us what the second one is. So a sub 1 equals 2, a sub 2 equals 5. I'm like almost halfway to figuring out what a sub 5 is. A sub 3 should equal a sub 1 minus 3 of those a sub 2's. A sub 3 should equal 2 minus 15. A sub 3 should equal negative 13. Sound okay?
Reeves, how do we know that's not multiplied?
How do we know what's not multiplied?
How do we know that a sub n minus 2 is not multiplied by that negative 3?
Because there's a minus sign there. They'd have to put like either some parentheses or a multiplication sign or something. A sub 4 should equal a sub 4 minus 2. Okay, that's a sub 2 minus 3 of those a sub 3's. That should equal 5 minus 3 of those. So really a plus 39. And a sub 4 should equal 44. And finally, a sub 5 should equal a sub 5 minus 2. So a sub 3 minus 3 of those a sub 5 minus 1, a sub 4's. And a sub 3 is a negative 13, and minus 3 of those 44's, 132, minus 132. Looks like minus 145 to me. Bear, she's in here. Okay, we've got about 10 more minutes left, and I think these are the last two examples. Yes. Hi, Bear. Yes, Harper's over here, hon. Where? She's in her chair over here watching some Baby Shark. A sub 3 equals those two put together, 2. A sub 4 should equal those two put together, 3. A sub 5 should equal those two put together, 5. A sub 6 should equal those two put together, 8. A sub 7 should equal those two put together, 13. A sub 8 should equal those two put together, 21. A sub 9 should equal those two put together. Looks like 34 to me. A sub 10 should equal those two put together. Looks like 55 to me.
Wait, isn't this like the...
Starts with an F.
I forgot what
FI?
it's called.
FIB?
Oh, Fibonacci.
There it is. This is the Fibonacci sequence. Thank you. It is a very famous sequence. Perhaps you saw it in a movie. No, perhaps you read about it in a book. Anyone ever seen the Da Vinci Code? Yes. Owen's nodding. Yes. Owen, did you watch the Da Vinci Code?
No, just I heard it in school in like 7th grade or something.
Lame to very lame. All right. Well, school is cool too. Yeah, it was in the book and the movie Da Vinci Code. None of you guys have seen the Da Vinci Code, huh? No. Sad.
Isn't it like everywhere somehow?
The Fibonacci sequence does crop up in all kinds of strange places.
Flower petal. It's super weird.
Yeah, there are a ton of examples. And what was really fun for me, when the movie The Da Vinci Code came out, it starred Tom Hanks. And that particular year, one of his sons was in my class. And although sometimes not such a stellar student, he really picked up on this Fibonacci stuff and gave us a ton of kind of cool examples. I kind of think our brains might be full. This was a lot of stuff that we did today. Not to mention I've got 1.5 screaming babies in here. Harper, did you want to say hi to everyone? And I don't know if you can hear it, but apparently someone's gardener just showed up. It could be mine, it could be my neighbor's. I don't know. It's kind of getting loud in here. What do you say we skip example 11 and Maybe I put it on Footage Friday, or maybe we just kind of don't see that one. We okay with that? I got some thumbs up. There, I got some responses for it. Yay! Alrighty, everyone. Then I guess we are going to call it a day. Let me do a